Hey folks, welcome to 6.2. We're going to increase our complexity here with angular momentum. 6.1 and energy was new topics, but something we'd covered most of already in the energy unit, whereas angular momentum is totally new. So we're going to do a lot of reviewing in this first video and connecting it to our new ideas. So angular momentum and impulse is our first topic. Our review is just to review linear momentum. So linear momentum is something that we said was basically like how much motion is happening in a system. Another more relatable way of defining linear momentum was how hard would this thing hit me if it hit me, or how much would it hurt. Linear momentum, P, equals mass times velocity. It is a vector, and so objects that are traveling in different directions have different momentum values. Same magnitude potentially, but different direction. We also learned about impulse. So in order to change the momentum of an object, you had to exert a force on that object over some amount of time. So delta P is our standard variable for impulse, and that's equal to the magnitude of the force acting on the object times the time over which it acts. We had a capital letter J for impulse, but there's no analog for angular momentum, so we're not going to have that in there. So P and delta P. So momentum and then impulse is how you change momentum. Angular momentum is essentially the same thing, except now it's rotation. It is how much rotational motion is there in an object or a system, and as with linear momentum, there are two factors. I suppose you can also think of angular momentum would be like how hard would this thing hit me if it rotated into me. Anyway, the variable for angular momentum is a capital L, also a vector. And you can probably guess what the variables are going to be for angular momentum. It's the analogs for mass and velocity. So that would be rotational inertia and angular velocity. So angular momentum is rotational inertia times angular velocity. That would put it with units of kilogram meters squared per second. And so how big is the object and how much inertia does it have times its velocity. And that's also a vector. So clockwise and counterclockwise rotations for velocity also determine the direction for angular momentum. It also takes an impulse to change angular momentum. So angular impulse, delta L. Again, everything is analogous. So in order to change the angular momentum of an object or system, you need to exert a net torque on it over some amount of time. So the second equation that we're learning today is angular impulse. So angular momentum can be changed as long as there's a torque acting on a system over time. The last of the basic reviews before we get into specifically angular momentum is we had graphs of force versus time in the momentum unit, and the area underneath a force versus time graph was going to show you the change in momentum, or the impulse on the object. Well, that is also true for graphs of torque versus time. The area under that graph is the change in angular momentum, or the angular impulse. So just watch out for graphs. At this point in time, the rotation unit is quickly doubling the number of graphs that we will have to deal with as physicists here. All right, the next part is just the impulse-momentum relationship. I don't have anything special to say about this, because again, it works the same way. If a torque is exerted over a certain time, then the angular momentum will change. So basically, if I put these two equations together, the torque acting over time is going to cause a change in angular momentum. Now, the way that we're dealing with this is that torque is only going to change the angular velocity. We will also think about situations where the rotational inertia itself changes. We haven't talked about really changing the mass of an object, but because rotational inertia has to do with how mass is distributed, that can change as objects move around. Okay, the last part of this video is a little bit confusing because, as it turns out, there's two ways that an object can have angular momentum. The simple way is that it's an extended object in rotation. Remember, extended objects are just like large objects that rotate, where their mass is distributed throughout themselves, instead of a point mass, where there's a mass in a specific location instead of distributed. So that's the easy one. We've talked about rotational inertia and angular velocity, and so there's nothing more to talk about other than these objects also have angular momentum. The other way to have angular momentum is to be a particle within a rotating system. Now, you can be as arbitrary as you want. You can say that any object moving in a linear fashion is actually part of a rotating system, as long as you define where that rotating system's axis is. And so we'll talk about that in a second. Particles that move in straight lines have linear momentum. And so if we extend our analogies here, angular momentum is going to be the distance that that object is from the axis of rotation times its linear momentum. And this is two vectors being multiplied, just like torque. And the more angular momentum an object has, or rather the amount of angular momentum an object has, depends on these three values, as well as the angle between the two vectors. And so you can see, much like torque, because of this sine function, what you can infer is that the more perpendicular these two vectors are with each other, the greater the angular momentum they will create. So we'll look at two examples. This first example is kind of easy to digest or believe, so to speak. We have a satellite in a circular orbit around a planet. Because it's a circular orbit, there's a constant value of r, the distance between the planet's center and the satellite's center. There's therefore also a constant speed because it's a circular orbit. And because it's a circular orbit, the angle between these two vectors is always going to be 90 degrees. So the angular momentum of this satellite is just going to be r times mv. And so that's nice and simple. Constant distance away and constant momentum, or constant magnitude of linear momentum. This second example is a little more mysterious because this mass is moving in a straight line toward the middle of this bar. And we're going to consider that this mass has an angular momentum. And we just need to figure out what that is. So, what you had probably tried to do in some torque problems is draw a line from the axis to the object, or rather to where the force was, and then to try and find the angle between that line and the direction of the force. You could do the same thing. You could figure out this distance. You could figure out the angle between them, and then you could calculate the momentum. In this situation, you can't, because in no situation would you be told where that object is. What's actually really interesting is as this object flies toward this point, it actually has a constant angular momentum because of how the variables change. The way that I want you to calculate the angular momentum of a particle is to draw a line that extends the velocity vector until it gets to a point where r and v would be perpendicular. And so we're going to consider that this mass exists right here inside this bar. That's going to create a value of r that goes straight through the middle of the bar. And then that velocity vector, assuming it hasn't changed, is going to be in the same direction and the same magnitude. And that's going to create a right angle. So even though this object is moving and its value of r, strictly speaking, is changing, we can model it as if it's permanently at this position where the velocity is directed perpendicular to the bar, and the r value is measured from the axis to that point. So using the variables that we have the length of the bar as L, we have this distance here as d, the angular momentum would be d times mv, according to this diagram. So that's what I want you to do when you're thinking about the angular momentum of an object that's traveling within a rotating system, is extend that velocity until it essentially hits the object. We're going to focus on collisions again, and then figure out the vectors. And that's that.